today's class is on analytic geometry, but before we get to that, we're first going to review last week's problem of the week. So let's go right ahead and do that. So this is last week's problem of the week. It's a bit long. I'll give you a few moments to read it in case you didn't. And feel free to type any ideas in the chat. So does anybody have any ideas? Yeah, radical axis certainly is an idea, especially since it was the topic of last class. So let's see how to do that. So the first thing we note is that IK is actually a pretty strange length because K and I are not very related. So we want to find a quantity we can use we can compute easily, which can find IK. So can anybody tell me what this quantity should be? K is the intersection of the B-midline of BDF and the C-midline of CDE. Do people need me to go back to the question statement for a moment? But actually this question, the answer should be the same no matter which point I'm talking about. So the point is that we want to find a length IK, and I is the center of a circle. And we already know the radius of the circle. It was given in the problem to be 10. So something we can do is instead compute the power of K, because we know that the power of K is just Ki squared minus 100. So if we know what the power of K is, we also know what Ki is. So now, what tricks have we learned to compute power? Well, as Kevin said in the chat, we can use radical axis. So can anybody find anything about radical axis and the point K? So it might seem a bit strange to be applying radical axis here because radical axis requires at least 2 circles and we only have 1. So we need to be slightly more creative in our application. So does anybody have any ideas on how to find radical axes which pertain to K? The circumcircle is a good guess, but K I do not think lies on the radical axis with the circumcircle and incircle. Yep, as Kevin says, K actually lies on the radical axis of the point B and the circle in the incircle. So basically, what we're using here is that points are just very small circles. So we can assume that we can still define the radical axis of a circle and a point. In this case, remember that the radical axis always bisects the common external tangents. And the common external tangents between B and the incircle are just BF and BD. So the radical axis of the point B and the incircle is just the B midline. Does that make sense? In a similar vein, we actually have that the C midline is the radical axis of triangles. The C midline is the radical axis of point C and the incircle. So that means that point K is actually the radical center of the three circles defined by the incircle, the point B, and the point C. So now, what's an equivalent expression for the power of K with respect to the incircle? Remember, the definition of radical axis is that points on the radical axis have equal power with respect to both circles. So remember, we want to compute the power of K with respect to the incircle. But K lies on the radical axis of point B and the incircle. So what does that tell you about the power of K with respect to point B? Yep, they're the same. So what we have is that Ki squared minus 100, which is the power we want, is actually just equal to Kb squared. So all we want to know is actually Bk squared. Oh, I skipped a tiny step here. So actually note that B and C are, K lies on the radical center of B, the incircle, and C. So its power with respect to B and with respect to C is actually the same. So Bk equals Ck, and K lies on the perpendicular bisector of BC. So with this in mind, we just have that Bk squared is 49 squared plus D squared by Pythagorean theorem. 49 is 1/2 the length of BC, since K lies on the perpendicular bisector. Is this making sense so far? Okay. So now we reduce the question to finding B. Why is K the radical center? So the B midline of BFD is the radical axis of point B and the incircle. Does that make sense? So because the midline of triangle BFD bisects the external tangents between the incircle and point B. So the midline is actually the radical axis. So K lies on the radical axis of point B and the incircle. Likewise, K lies on the radical axis of point C in the incircle. So since it lies on the intersection of the two radical axes, it has to be the radical center. And as a corollary, this means that it lies on the radical axis of point B and point C, which is just the perpendicular bisector. Does that clear things up? Okay, so let's move on. Now we just need to find the distance D. So how can we do this? First of all, note that besides the fact that they're radical axes, we haven't actually used much about the midlines. In fact, there's another very nice property about them. In particular, can anybody spot any lines which are parallel to the midlines? In particular, the B midline, for example. Yep, the external angle bisector is parallel to the midline. And one way to see this is that the midline is, since BFD is isosceles, the midline is perpendicular to the angle bisector of angle ABC. And we know that the external angle bisector is also perpendicular to the angle bisector. So BIA is parallel to the B midline. So that's pretty neat. Likewise, we have that the C midline is also parallel to the C angle bisector. I mean, the C external angle bisector. So now that we have this, we can try to compute the distance from K to BC. So does anybody have any ideas on how to do that? Well, first of all, does it look like there's any points are collinear in our current diagram? Yep, DK and the angle and the AX center look collinear. So let's try to prove that. First of all, where does the B midline intersect line DIA? Yeah, the midline is going to hit it at the midpoint. Because if we look at triangle DBIA, the B midline is parallel to BIA, and it also bisects the line BD. So it's actually also a midline of BDIA. So this tells us that the B midline is going to hit DIA at the midpoint. How about the C midline? Where does the C midline hit DIA? Well, of course it's symmetric, so it's actually going to hit the same point. So this tells us that the B midline and the C midline actually concur on line DA. Oh, that's a typo. It should say DIA, not DIB. So this tells us that K is the midpoint of line DIA. So now can anybody think of a nice expression for D? Yep. The length D is actually the AX radius over 2. And the way to see this is that since K is the midpoint of DIA, the distance from K to BC is half the distance from IA to BC. And the distance from IA to BC is just the AX radius, which tells us that the distance from K to BC is half the X radius. Does that make sense? Okay. So now we're at the final stage. Now all we have to do is calculate the AX radius. And the problem gave us already a lot of information. So let's find out how we can do this. Does anybody have any ideas? So if we take IA and take its perpendicular to AB, let it be X, we actually get some similar triangles. If we look, we have the triangle IFA is similar to the triangle IAXA. So using this diagram, can somebody tell me what the X radius should be in terms of the sides and the inradius? Well, by similarity ratios, we have that the length IAX, which is the X radius, is just IF, which is the in radius, times AX over AF. So do people know what AF is? Remember, F is the in touch point. Yeah, so AF is S minus A. And the way we can easily prove this is that like AF is equal to AE, BF is equal to BD, CD is equal to CE. So we set up some equations in terms of these three variables to get that AF is S minus A. So in a similar way, we can set up these three equations for an X circle to get the lengths of the tangents from A, B, and C to the X circle. In particular, if you do this, we won't show the calculations here. AX is actually equal to the semi-perimeter, is equal to S. So now we can use the similarity to find RA. In particular, RA is going to be S over S minus A times R. And do we know all these values? So we obviously know R is 10, but how about S over S minus A? Well, remember from the beginning that our the question doesn't only say that BC is equal to 98. We actually have that AB plus AC is equal to 3BC. So given this, can anybody find the value of S over S minus A? Remember, S is just the semi-perimeter. Yep, it's 2. So how to see this? S is equal to AB plus AC plus BC all over 2. And AB plus AC is 3BC. So this quantity is just BC plus 3BC all over 2, which is 2A. So we have that S over S minus A is just 2A over A, which is 2. And RA is equal to 2R, which means that D is equal to R. So remember that when we got D, now all we need to do is compute BK. BK gives us the power, and the power gives us IK. So let's just reverse all the steps we did to get here. So first, BK squared is going to be equal to 49 squared plus D squared. And D squared is R squared, so it's 49 squared plus 100. And this is the power. The power is Ki squared minus R squared by the formula for power. So now rearranging, we have Ki squared is equal to 49 squared plus 2R squared. So Ki is equal to the square root of 49 squared plus 200, which comes out to 51. And that's our answer. So that was a pretty long and involved solution. Does anybody have any questions about any part of this? It looks like no, so in that case, we'll move on to today's topic, which our first part is going to be about Cartesian coordinates. So we won't go into depth about like the definition of Cartesian coordinates, since I'm sure many of you know them already. So instead, we'll present you a list of tricks to help make your coordinate bashes faster. So one thing you guys should always do is first and foremost, identify from the beginning if the question is feasible to coordinate bash. So a lot of people, when they look at a geometry question on the AMY, immediately turn to bashing. And this is the wrong mentality. You should only bash if you know that it's going to be faster than, say, looking for a synthetic solution. For example, if the question has a number of angle conditions or nonlinear intersections, such as the intersection between two circles, it's probably not the best question to coordinate bash, unless you first make a number of synthetic observations. So once you've determined that the question is coordinate bashable, the next thing you want to do is to look for a good origin and good axes. So not all coordinate bashes are the same. You first need to define the origin and the axes. So for the origin, you always want to define a point which is used extensively. For example, lines passing through the origin are of the form y equals mx, which is nicer since it doesn't have the b term. So if there's a point where a lot of lines are going through, set it as the origin. And if there's two prominent perpendicular lines, definitely use them as axes. But if there's only one, make sure to set it as one axis. And generally, if there's only one prominent line, we'll just set it as the x-axis for convenience. And after this, you want to always be smart when bashing. So oftentimes bashes can be very long and tedious. So before you begin bashing, make sure you have a method in mind which guarantees a correct solution and uses minimal computations, which leads us to our last point. Always look for synthetic observations first before bashing. For example, if we prove a collinearity or concyclicity before beginning to bash, it can decrease the computation time immensely. And now that we know all these tricks, we might as well also review some of the most commonly used formulas when coordinate bashing. So we'll breeze through most of these since most of you already know them. The equation of a line, y equals mx plus b. The distance formula is d squared equals x minus x naught squared plus y minus y naught squared. And we also have that parallel lines have equal slope and perpendicular lines have slope which multiply to -1. We also have the slope of a line which hits the x-axis at an angle of theta is tan theta. So this one you guys may have not seen before. It's pretty easy to prove. Just drop it down and use trigonometry. And we also have that the distance from a point to a line, from a point x naught y naught to a line ax plus b y plus c equals 0 is of the form d equals the absolute value of plugging in the point into the line equation and then over square root a squared plus b squared. And finally, when we want to compute areas in coordinate bashing, we use the shoelace formula, which states that if you have a polygon P with vertices A1, A1, B1, A2, B2, all the way to A and Bn listed in their order, then the area of P is going to be 1/2 the absolute value of the products A1, B2 plus A2, B3 all the way to AN, B1 minus all the products B1, A2 plus B2, A3 all the way to BN, A1. And it's a bit hard to explain here, but the reason why shoelace formula is called shoelace formula is because if you write all the points down vertically, the products can be expressed as diagonals in the vertical list, sort of like lacing a shoelace. So this will be explained in a bit more depth in the handout, but yeah, it's shaped like a shoelace. But I'm sure a lot of you have already seen it and have already drawn the shoelace before when doing coordinate bashes. So without further ado, let's move on to our first coordinate question. And this is from 2017 AMY 2, number 10. And I'll give you a few moments to read the question and feel free to type any ideas in the chat. In particular, type what do you think our setup for coordinate bashing should be? Yep, there are a lot of synthetic observations you can make, but we're actually just gonna coordinate bash this straight. So it looks like people already have a lot of good ideas in the chat. Do we need a few more moments to read? Looks like no. So as people said, we should set D as the origin when we're coordinate bashing. AD will be the y-axis and CD will be the x-axis. And given this setup, which points do we know the coordinates of immediately? Yep, so we just know all the points on the sides. We know D, C, B, N, A, and M because all their values were given. So the values are displayed on the screen. This is just coming straight from the definition of coordinates. So using these, we can now compute our two lines, lines DN and CM. So can anybody tell me their equations in the chat? Yep, so dn is equal to y equals 3 halves x, and this just is because it passes through the origin, so there's no constant term. And yep, I think that's right. Cm is going to be x plus 4y equals 84, and we can also write it in slope-intercept form as y equals -1/4 x plus 21. So now intersecting them is going to give point O. So we just set the two right-hand sides equal to each other to find the x coordinate for O. Can anybody tell me what that should be? Okay, somebody had the idea of finding the area of DPC by computing the side lengths using Pythagorean theorem, and then I think probably using Heron's next. So this is a way to compute the area, but actually we're just going to find the coordinates of P. Because once we do that, by the virtue of coordinates, we already know the height from P to CD, so we can just use 1/2 base times height. So that's going to be the general structure of our solution. But first we need to find O, and as people have said in the chat, O has x coordinate 12 and y coordinate 18. So now we have O, we have all four coordinates of the quadrilateral BCON. So we can compute its area. So what should we do to compute its area? Yeah, shoelace is a good idea, but we can actually be a bit more clever here. Note that BCON is actually the trapezoid BCDN minus the triangle ODC. And we already know both the area of the trapezoid and the area of the triangle, because the trapezoid can be just computed by 56 plus 84 over 2 times its height, which is 42. And we know the height and the base of the triangle is 1/2 84 times 18. And crunching the numbers, we get 2,184. So given this, what's the area of BPC? Actually, there's a small technicality. The question said that P had to lie on the side lengths of the quadrilateral, so it could technically lie on ON as well. Except it's pretty easy to show that it lies on OC. So just take our diagram for granted. Yeah, so the area BPC is 1/2 of 2,184, which is just 1,092. So now how can we find the coordinates of P given this area? Yep, so BC is the base. Naively, we could probably assume it has coordinates X and Y and then use shoelace and then use the fact that it lies on CM. However, we see it, BC is just a base and the height from P to BC is sort of its X coordinate. In fact, it's 84 minus its X coordinate. So we know that BC has length 42 and the area of BPC is 1092. So the height from P to line BC is 2,184 over 42, which is 52. So given this, what's the X coordinate of P? Well, I just said it, it's gonna be 84 minus 52, which is 32. And now that we have its X coordinate, we know that it lies on Y equals -1/4 X plus 21. So its Y coordinate is 13. And now, given this, what should the area of DPC be? Yep, let's use 1/2 base times height. We know that the height is the Y coordinate P, which is 13, and CD is 84. So our answer is 1/2 84 times 13, which is 546. So are there any questions? Yep, this question is pretty misplaced. It's really easy with coordinates. And also, as people have pointed out, it's also not that hard with similar triangles. Well, it looks like there are no questions. I'm going to turn it over to Aditya to go over the next coordinate question.
All right, so I'll give you a couple of minutes to think about this and the setup for how we're going to go about finding the area of AEF. Okay, so let's get started. So I think people have a good idea of where to put our axes. So we'll let A be the origin, and then AD can be the x-axis and AB can be the y-axis. So we have these coordinates for A, B, C, D. And so the first thing we need to do is find the coordinates of P, because once we have the coordinates of P, then we can find E and F. So how would we go about finding the coordinates of P? Yeah, so P is on both of these circles, so we can just write both their equations. So the equation of T, which was the diameter, circle with diameter AD, is x minus 30 squared plus y squared equals 900. And the equation of S is x squared plus y minus 15 squared equals 225. And so notice that when we subtract these two equations, the x squared and y squared terms cancel, and so do the constant terms. So we end up with 60x minus 30y equals 0, or y equals 2x. Yeah, another way we can do this is by using the altitude, but I think both methods have about the same amount of computation here. So then once we substitute y equals 2x into one of these equations, it actually turns out being very simple, because remember that when we solve these equations, we're finding the intersection between these two circles, and the origin is also an intersection point. So whatever equation we end up with has to have x equals 0 as a solution. So we can solve this and get x equals 12. So that means the coordinates of P are 12 and 24. And note that the equation of line AP is y equals 2x. So can someone say what the coordinates of E are? Yep, so E is 1530, because the equation of line BC is y equals 30. So now we have to look at the tangency here. So we have EF is tangent to the circle with diameter AD, so we can let x be that tangency point. And there's a couple of ways we can go about finding the coordinates of x. And so we'll go through one way. So one way would be to find the length of EX, and note that then x would lie on a circle with center E and radius EX. And we can use the equation of that circle and the equation of the circle with diameter AD to solve for the coordinates of x. So the problem asks for the area of triangle AEF. So we have the coordinates of E, so our end goal is to find the coordinates of F as well. And to do that, we can find the coordinates of x. So yeah, EX turns out to be 15, because note that the distance from E to the circle from its tangents that's EX, but this is another tangent from E to the midpoint of BC, and since the tangents from E have the same length, and since BE was 15, the distance from E to this point here is also 15. So that means EX is 15. So that means that that means X is on a circle with center E and radius 15. And the equation of that circle is X minus 15 squared plus Y minus 30 squared equals 225. And remember that the equation of T, which was the circle with diameter AD, is X minus 30 squared plus Y squared equals 900. And we can solve this the same way we did before, by subtracting to get rid of the x squared and y squared terms. So if we simply subtract, we get 30x minus 60y plus 900 equals 0, or x equals 2y minus 30. So this relation for x can be substituted in either of the two circles we have, and that would give us a quadratic equation with y. And we can solve that to find the value of y. So if we solve this quadratic here, it factors as 5 times y minus 18 times y minus 30. But note that the y equals 30 point is actually this tangency point here. So our the coordinates of x are actually 6, 18. So the y coordinate is 18. And to find the x coordinate, we would do 2 times 18 minus 30. So x is 6, 18. And that means that, now we have E and X. So can someone say what the coordinates of F are? So remember, E was 15, 30. Yep, it's 0, 10. So if we use, if we find the slope intercept form of this line, it's 4/3 x plus 10. And so f is on the y-axis, so this is just the y-intercept. So f is 0, 10. And now how do we find the area of AEF? Yep, so it's just 1/2 base times height. So the base is 10 and the height is the x coordinate of E, or 15. And we get 75. So does anyone have any questions? So if you horizontally shrink this diagram, the circles turn into ellipses. So I mean, you can do it, but I don't really see the point here. Okay, so looks like there are no questions, so we will go to our last coordinate problem for today. So do people need more time to read the question? So to get started, first, like we should assess if this is a good problem for coordinates, and it probably is because we have some parallel line conditions and perpendicular lines too. So that's easy to work with slopes. So the next question is, where would we put the origin? So yeah, so some people said D should be the origin, and the reason this is a good choice is because when you set D to be the origin, basically most of the points we have would be on either the x-axis or the y-axis in this case. And that would make like a lot of the simplification much easier, especially the points x and y, which are basically, we don't know anything about x and y other than the conditions that x, y, and AO are parallel and OY and AX are perpendicular. So we'd probably need to set variables for those. So it's a good choice for D to be the origin in that case. So so how do we find the coordinates of A? Yep, so from Heron's, our area is 15√7/4, and that means our height is 2 times that over BC, and that comes out to 5√7/4. So that means A is 0, 5√7/4. And so in right triangle ABD, we have AD is 5√7/4, and AB is 4. So we can calculate BD to be 9/4. So that makes the coordinate of B to be -9/4, 0. And since BC is 6, we get C is 15/4, 0. So so now we would want to find the coordinates of O. So can someone say what the x coordinate of O is? Yeah, I think we should be a little bit careful because D is the origin and not B. So I think a few people said 3. But yeah, so that's the general idea. Since O is on the perpendicular bisector of BC, the x distance from O to B is 3. And since BD is 9/4, we have the x coordinate of O is 3 minus 9 over 4, or 3 over 4. So how would we find the y coordinate of O? Yep, so we can, so to find the y coordinate, we can actually just use the distance formula from between the, like the distance between O and B, because the distance between O and B is the circumradius R, and we can find R with the formula ABC over 4 times the area. So we get R is 8 over root 7. And then from the distance formula, we have 3 squared plus y squared is 8 over root 7 squared. And if we solve this, we get y is root 7 over 7. So we can conclude the coordinates of O are 3/4 and root 7 over 7. And now I'd also like to make a comment about E. So E is not really a relevant point in this diagram, because like none of the conditions we need later in the problem are in terms of E, and like, so we don't have, so there's no point in trying to find the coordinates of E now. So so now we can just set a variable for the coordinates of x. So x can be a comma 0. And so now we have to use both of our conditions. So let's start with xy is parallel to AO. So what does that tell us about the coordinate of y? So first, what's the slope of AO? Yep, so the slope of AO is root 7 over 7 minus 5 root 7 over 4 divided by 3/4, and that comes out to negative 31 over 21 times root 7. And since the slope of xy has to be the same, and we set x to be a comma 0, this means that y has to be 0 comma 31 root 7 over 21a. So we can verify that now xy has the same slope. So now we have x and y in terms of this variable a, and we have one last condition, ax is perpendicular to oy. So we'll use that to solve for the value of a. So so first we have to find the slope of oy, and or first we'll do the slope of ax. So the slope of ax is 0 minus 5 root 7 over 4 divided by a minus 0. So that's negative 5 root 7 over 4a. And then the slope of oy. Yeah, it's a little bit messy, but it's not too bad. So the slope of oy is root 7 over 7 minus 31 root 7 over 21a divided by 3/4 minus 0. So if we simplify a little bit, this turns out to be 4 root 7 over 63 times 3 minus 31a. And now we remember that the condition for perpendicular lines is that the product of the slopes is -1. So this means that we have this result. And so now a lot of the constants cancel, and we end up with 5/9a times 3 minus 31a is equal to 1, or 15 minus 155a equals 9a. So we can solve to get a is 15/164. But remember that this is not the final answer. A is actually the x-coordinate of x, which is the length dx. And we want the value of bx. So we have to add BD, which was 9/4. So once we add this and simplify, we get our answer of 96/41. So does anyone have any questions? Okay, so now we're going to have a break for 5 minutes.
I guess we'll get started with the other topic for today, which is complex numbers. So complex numbers are like another way to do geometry problems analytically, like as an alternative to Cartesian coordinates. So so what do we mean by when we use complex numbers? Well, so in Cartesian coordinates, we express everything as an x and a y. With complex numbers, we're going to express everything with a single complex number where, like, for example, the x coordinate is the real part and the y coordinate is the imaginary part. You could think about it, right? So so what are like, so that makes them very similar in this way, right? But what are the advantages of complex numbers? Like, why would we use complex numbers over Cartesian coordinates? Is because like complex numbers are especially nice for rotations, right? So in particular, if you have a point, like let's say z, and then you want to rotate it by like an angle theta about the origin, then you just have this nice expression that's just a multiplication by z. All right. And then so why is this true? Right. Well, you can remember that what happens when we multiply two complex numbers is basically their magnitudes multiply and their arguments add, right? Arguments being like their angles, right? So and then clearly cosine theta plus I sine theta has a magnitude of 1 and the argument is theta, right? So that's why that works. So now what if we wanted to say rotate about a point that isn't the origin, right? Well, how would we do that? Well, then what we could do is we could basically shift it so that whatever point we're rotating about becomes the origin, right? So we like, what does this expression mean? Basically, like when we shift a to be the origin, well then, yeah, exactly, we shift it to the origin so that like a goes to 0 and z goes to z minus a, right? And then we can do the same rotation operation that we saw on the last slide, where we just multiply it by cosine theta plus I sine theta, and then we shift it back by adding a again. Right. So so then this can give you like our desired expression, right? So, well, this is not unique to complex numbers. Like we can do the same with Cartesian coordinates. by just like, you could, for example, see this by plugging in z equals x plus yi, I mean, and then just seeing the things work out. And then like it is basically the same thing, right? But the difference here is that it's more natural to see in complex as opposed to Cartesian, right? So yeah, and then I guess that's like review of complex numbers, and then we'll have enough to move on to our problems. Our first problem about, yeah. So here's our first problem. And then, yeah, if you have ideas, you can send them in chat. Yeah, so we have people saying basically like you see that you have this equilateral triangle, and then equilateral triangles are basically rotations by 60 degrees, right? And then that's how we would use complex numbers here, right? But so someone also suggested like coordinates, right? So we are actually going to be using coordinates, but like this is basically the same in both of them. But like we see that we have a right triangle, we have and then like we just learned how to do rotations in both complex and coordinates and Cartesian, right? So we're just gonna use Cartesian on this question. Right, so let's just first set up our axes. So like I saw someone already said we want C to be the origin, right? Because it's a right triangle and you almost always want the right angle to be at the origin. And then so that you just let CA be the x-axis, CB be the y-axis. And then, well, P and Q are just arbitrary points on the triangle, on the two sides of the triangle, right? So let's just, that means that they're on the axes. So let's say like, let's just give them coordinates. So now like, how would we find R? Exactly. R is a 60-degree rotation of Q around P, right? So yeah. Now, how do we find out what point this is, right? Well, we would have to translate it so that P is the origin, right? And then we had an expression for what it was, like for what the rotated point would be. And then, so we see that we need cosine and sine, and then we plug everything in. And then so that is our rotated Q prime, right? And then we remember that we want rotated Q, right? So we want to shift back So we like add P again, and then so that gives you the location of R. Right. So now the requirement that we have on R is that it needs to lie on AB. Right. So what is the equation of AB? Yeah, I think that looks right. Yeah. So you could write it that way. You could also just write it as like ax plus by equals c, like 2 root 3x plus 5y equals 10 root 3. But yeah. So now, well, now what do we do with this equation? Yeah, so we just plug in R's coordinates. And then so we have that. And then we simplify it. And then so we have this equation. Right, so now we want to remember what we're trying to find, right? We're trying to find the minimum area of PQR. So how would we find the area of PQR in terms of P and Q? Yeah, so a side length would be square root P squared plus Q squared, right? Because that's just the distance between P and Q, right? So yeah, so that should say PQ squared equals P squared plus Q squared instead of X squared plus Y squared, but the idea is the same, right? So, and also that should say the area of PQR is root 3 over 4 times P squared plus Q squared and not root 3 over 4 times the area of PQR. But yeah, so basically we want to minimize P squared plus Q squared while subject to the condition of 11p plus 7 root 3q equals 20 root 3. Right, so how do we do this? Yeah, Cauchy is probably the easiest way to do it, right? So we just set up like a Cauchy inequality, and then basically Cauchy just gives us directly what we want, right? We have stuff in terms of P squared plus Q squared on one side and stuff in terms of 11p plus 7 root 3q on the other side, right? So now all that's left to do is just solve for P squared plus Q squared. So then you just get P squared plus Q squared is at least 300 over 67, right? So then you can check like that this is actually satisfiable because like Cauchy also happens to give you when you have equality case. right? So like, you would have equality case when like the ratios are equal, right? So yeah, and then all you have to do now is just plug in, like, remember that the area is √3/4 times p squared plus q squared, and then that gives you your answer, and then you just add up the things that you like, 75 plus 3 plus 67, and then that gives you the answer. So do we have any questions on that? Oh, what is Cauchy? So Cauchy-Schwarz is like an inequality. Basically, it's an inequality that it's basically just an inequality. Yeah, you have a, like, for example, in this case, you have like a squared plus b squared times c squared plus d squared is greater than or equal to ac plus bd squared. Yeah, exactly what Daniel said in chat. Yeah, so yeah.
Okay, so our next problem, which will be purely complex numbers this time, no coordinates, is this theorem called Napoleon's theorem. Diagram should be fairly self-explanatory. Just a heads up, it won't be on the remaining slides, so be sure to get it down. As a fair warning, the proof I have on the slides is a bit messy. I'd encourage you to try to work it out on your own paper as well. Does everyone have the statement of the theorem as well as the labeling of the points, which is important? Does anyone need more time? Yep, the inner Napoleon triangle will be a homework problem. Yeah, it is. Just some extra practice. Okay, I guess we can move on to the calculation. So with complex numbers, when we denote the coordinates of points, we typically just use the corresponding lowercase letter. So the complex number corresponding to point A is going to be lowercase a and so on. So now we have an arbitrary triangle ABC. So let's let the coordinates of the vertices be ABC, as shown in the diagram. Well, then the rest of the coordinates are uniquely defined. So let's try to calculate everything in the problem in terms of A, B, and C. And once we get all the points down, we can try to show that it's equilateral. So let's get started. How can we express the point D? We have an equilateral triangle BCD, and where we have coordinates B and C. And now expressing the third vertex of the equilateral triangle should be pretty similar to the previous problem. Any ideas? To get D, D is outside BC. It's triangle BCD. So we can get D when we rotate the vertex B about C 60 degrees counterclockwise. So in the diagram we had before, triangle ABC, the vertices ABC were labeled counterclockwise. So in this case, D is the image of B under a 60 degrees counterclockwise rotation around C. And with this, we can write the expression for D. We know the rotation formula, so let's write D in terms of B, C, and trig functions of 60. That ends up looking like this. We have the cosine 60 plus I sine 60 rotation and the points getting shifted. Well, we know cosine 60 should be 1/2 and sine 60 should be √3/2. So now we can get rid of the trig functions, just write it like so. And for this problem, what we have here is our free variables A, B, and C. So what's typically helpful is to group the terms by variable. So instead of what we have here, where there's a mix of B and C on the first term and then just C in the second term, let's try to get it to constant times B plus constant times C plus constant times A if necessary. This is just cleaner to manipulate. If we do that, then we can get 1/2 plus √3/2I times B plus 1/2 minus √3/2I C. Does everyone see how we can get this? We take the minus C out of the first factor and group it with the second term. So now that we have D, how are we going to get X? X is the center of equilateral BCD. What can we say about the coordinate of X? Yep, since X is the centroid of triangle BCD, X should just be the average of B, C, and D. So X is 1/3 of B plus C plus D. And now we have D in terms of B and C. So I'll just give you a little bit of time to check it, plug it in. It should work out to so. Cool. So now we have the coordinate of X, which is one of the 3 vertices of the triangle we want to show is equilateral. Now we need to get Y and Z. So we can do the same thing if we want, and we can get the coordinates of Y and Z. Or under a contest setting, you could just say we shift the variables. So you can get analogous expressions for Y and Z just by shifting variables like so. So you see, to get from X to Y, you just send B to C and C to A. And then for Z, you shift the variables one more again. So now we have X, Y, and Z in terms of A, B, and C. Does anyone have any questions up to this point? If not, then let's get on to the second part of this problem. Now we want to show that triangle XYZ is equilateral, given their coordinates. How can we do this? Well, in general, showing that 2 segments have the same absolute value for in complex numbers is quite difficult. It's because the absolute value function doesn't behave super well. So yep, that's a better suggestion. Since we know that an equilateral triangle has 60-degree angles, we can do the same thing we use to compute the coordinates using equilateral triangles. If we can show that when we rotate y 60 degrees counterclockwise around x, the image is z, that automatically implies the triangle is equilateral. Does everyone see why? Also in chat, find the ratio z minus y over x minus y. Yeah, it should be cosine I sine 60 degrees. And explain how to show that triangle XYZ is equilateral. So if we have a triangle XYZ, and now we rotate it 60 degrees counterclockwise around x. If we can show that y goes to z, that automatically implies the triangle is equilateral. The rotation tells you that xy equals xz. And since the rotation is 60 degrees, we know that angle x is 60 degrees. An isosceles triangle with 160-degree angle is equilateral. So this part might get a little bit messy, but now that we have the coordinates of x, y, and z, let's plug everything in. In order to show, it's not that messy, but I think it could be a bit neater. I didn't really do it the most concise way. Let's first write the expression. So if we can show that this is true, then we'll be done. We can conclude that is the rotation. So let's compute the right-hand side first. We know what the left-hand side is already. We have the coordinates of z. So we'll just have to expand the right-hand side. So let's go through it step by step. We have our expressions here for y, x, and y. So let's calculate y minus x first. Okay, yeah. Let's see. I think we have a typo here. It should just be y minus x on the left-hand side. And it's a lot easier to see this when we have our expressions for x written like so. Something times b plus something times c. Because then you can just compare, add, subtract the coefficients of b and c and a, rather than trying to expand everything. Now we need to multiply this by cosine I sine 60 degrees. Cosine I sine 60 degrees is 1/2 plus root 3 over 2i. And once again, we can just multiply each coefficient by 1/2 plus root 3 over 2i, since we have it written nicely in this form. So I'll just gloss over the calculation here. But if we multiply the first coefficient, we get that. If we multiply the second coefficient, then we get minus root 3 over 3. If we multiply the third coefficient, root 3 over 3, we get minus 1/2 plus root 3 over 6x. And now all we have to do to get the final expression is to add x. We have the expression for x in the 5th bullet. And once again, the coefficients make it easy to see how to get x. We add the coefficients for b and add the coefficients for c. And then the final expression for the cleaned up right-hand side is this. And that's perfect. This is exactly z. So we can conclude that z is the image of the rotation, and that means triangle XYZ is equilateral. Does anyone have any questions about the second half? I did go fast over the calculations because they're not particularly enlightening, but we have the second Napoleon, the inner Napoleon triangle as a homework problem, so you can try your hand at doing a very similar calculation. If there aren't any questions, then we can move on to the last problem of the day. Sorry, what is the question? When do you do complex bash mean? I I can think of multiple interpretations, so I'm not sure which one to answer. So if you're asking when you would use complex numbers in general, on the AMY, I think the uses are mostly rotation based. So if you have an equilateral triangle, that's a big tip off. And if you have a rotation in general, we have one homework problem where you rotate the coordinate axis. So yeah, if you have a rotation complex and you want to use some sort of bash, complex numbers are good at representing rotations. Yeah, so a bit of preface for this last problem. As you may or may not be aware, complex numbers are a super useful tool for Olympiad geometry problems. They can be used to bash all sorts of hard IMO questions, even the last problem of IMO 2019. And they're a general geometry tool in general, but their uses on the Olympiad are quite different from their uses on the AMY. So this problem is just a sample of some of the ways that you can use complex numbers on Olympiads. We'll be using one formula, the tangent intersection formula, which you might not see on the AMY, but you might see if you want a complex bash problem. And this is a really hard problem. So this is just more of an enlightening example rather than something intended for use on the AMY. This is the last problem on the geometry test. So with the diagram shown, let's jump into the problem. So one thing about complex numbers in Olympiad geometry is that the complex numbers on the unit circle behave quite nicely. In the test, they do not give the diagram. This diagram isn't to scale either. This is just a nice diagram for explanation purposes. The reason to use complex numbers here are pretty different from those on the AMY. In general, when you see a quadrilateral with an inscribed circle on an Olympiad contest, you might want to set that inscribed circle to the unit circle. So the explanation here is that complex numbers on the unit circle behave nicely. And we have a good circle that we can set to be the unit circle here. The unit circle, sorry, I didn't explain. It's the circle of radius 1 centered at the origin. So let's get started. So suppose the incircle touches the sides at WXYZ as shown. We would like to be able to set the incircle to the unit circle because then WX with the complex numbers WXYZ behave nicely. But unfortunately, the lengths we're given make this impossible. We're given lengths in the teens, and that won't work out for the unit circle. However, what we want to find in the end is the ratio IM over IN. So if we scale this diagram, if we zoom in or zoom out, that won't affect the ratio. It'll affect the individual lengths, but the ratios will still stay the same. So let's just assume that we scale this diagram so that the incircle is the unit circle. Yeah, so the nice property about complex numbers on the unit circle is that their conjugate is their reciprocal. Normally, you would need two variables to describe a complex number, z and z bar. There's no way to easily express z bar in terms of z without introducing other variables. But when a complex number is on the unit circle, you can represent z bar by just 1 over z. And that's why the unit circle is, the complex numbers on the unit circle are nice. So as noted earlier, since we want the incircle to be the unit circle, and all we're looking for is a ratio, let's just shrink everything down to the unit circle. In particular, the lengths IA, IB, IC, ID, which we were given, they'll change, but they'll change in the same ratio. So if the scale factor is k, then we can just write 12k, 16k, 14k, and 11k. So any questions so far? This first slide was basically just an explanation of it would be nice if the incircle is the unit circle, and since we want a ratio, let's just scale it down to the unit circle. So the next slide is a formula that we'll use to convert to the unit circle. On the third bullet, that's the nicest property of complex numbers on the unit circle. Their conjugate is 1 over themselves. And you can check this by multiplying both sides by z. Then z bar should be the absolute value of z squared. But on the unit circle, the absolute value of z is 1. So you have this formula shown. So let's jump into the formula that we'll be using. So we're going to be using complex numbers wx, y, z because they're on the unit circle. In order to find a, we're going to be using this formula. Now, what is a in terms of w and z? Is the intersection of the tangents to the unit circle at w and z. You can see that AW is tangent to the unit circle and AZ is tangent to the unit circle. So this uniquely defines A, and this formula lets us calculate what A is. So in order to find it, let's first we can erase the other points because they're not important. And let's just draw the diagram shown. In particular, you can see by symmetry that P should be the midpoint of WZ. AW is equal to AZ because they're both tangent to the unit circle. IW is equal to IC because they're both radii. And then PW equals PZ by construction. So line API should be the perpendicular bisector of WZ. Does everyone see why this is the case? So now we know that API are collinear. What this means is that P lies on ray IA. It tells us that A and P should have the same argument. In particular, the arguments are the same and not a 180-degree shift of each other because they lie on the same side of I. Also note that triangles AWI and AZI are right. This is just because of tangencies. So now in this diagram, we have a lot of similar triangles, and go to the details, but you can get that IP times IA should be equal to IW squared. You have some similar right triangles here. So that means that IP times IA is equal to 1. What does this mean in terms of complex numbers? It means that the absolute value of P times the absolute value of A is 1. So as we mentioned earlier, IP and A are collinear, which means that they should have the same argument. Now, what's the argument of the conjugate of P? Well, we get the conjugate of P by reflecting P over the real axis. So the argument of P bar should be 360 minus the argument of P. And since the argument of P is equal to the argument of A, this is 360 minus the argument of A. And that means when we move everything to one side, we get that the argument of P bar plus the argument of A is 360 degrees, which is 0. And since arguments add when we multiply, that means the argument of P bar times A should be 0, What this means in particular is that P bar times A is a positive real number. Now let's return to the equation we have up there. IP times IA is IW squared, which is 1. Well, what does this mean in terms of complex numbers? That means that absolute value of P times the absolute value of A is 1. But the absolute value of P is the same as the absolute value of P bar, which means the absolute value of P bar times the absolute value of A is 1. So we have the whole chain of equalities here. The absolute value of P bar times A is the absolute value of P bar times the absolute value of A, which is the absolute value of P times the absolute value of A, which is IP times IA, which is 1. But the thing on the very left-hand side, we know that it has to be a positive real number and has absolute value of 1. What does that mean? The left-hand side is 1. So we know that P bar times A is 1. Does anyone have any questions up to this point? The proof of this lemma isn't terribly important to the rest of the problem. It's just a formula used, but we're including it for completeness here. So now we can write that A should be the reciprocal of P bar. But the conjugate satisfies some nice properties. So we know that P is the average of W and Z. It's the midpoint of WZ. So P is going to be W plus Z over 2. Now when we take P bar, it's going to be the conjugate of Z plus W over 2. And now by conjugate properties, it's Z bar plus W bar all over 2. But now we know that Z and W lie on the unit circle. And this is particularly nice. We can replace Z bar and W bar by just 1 over Z and 1 over W. And when we do that, we get the right-hand side. Now what we've had from what we had earlier, we know that A should just be 1 over this thing. When we do that, we get the formula. So that completes the proof of the tangent intersection formula. As stated earlier, it's pretty independent of the rest of the problem. It's just a useful formula for complex numbers in general. So let's get back to the main problem. So we know that A should be 2ZW over Z plus W. We have our new formula. And we can just do the same thing for B, C, and D. We have the similar expressions for B, C, and D. So we have all the vertices of the quadrilateral labeled now. So we can try to compute the other relevant points. M is the midpoint of AC, which means it's the average of A and C. And once we plug that in, we expand it. And N should be the average of B and D. We do that too. So now what's the quantity we want to find? We want to find IM over IN. Now IM is the absolute value of M, since I is the origin. And IN is the absolute value of N. So now we just want the absolute value of M over the absolute value of N. And by absolute value properties, it's just the absolute value of M over N. And now we can see that the apparently messy expressions for M and N cancel greatly. So we have this nice factored expression that we want to find the absolute value. And again, by absolute value properties, we have it's the absolute values of the individual terms multiplied and divided. Does anyone have any questions about how we simplified IM over IN or anything in general? now that we have an expression for im over in, we want to try to put numbers to it. And we haven't used our given lengths yet, 12, 11, 14, 16. So let's try to put them to use. So for this last step, we're going to be using the given lengths. Since IA is 12K, we scaled everything down. We know the absolute value of A is 12K. But we have a formula for A. It's 2ZW over Z plus W. And with absolute value properties, we can just break down the product and quotient of absolute values. But we also know that a Z and W lie on the unit circle. So we can get rid of those absolute values. They're 1. So that just means the absolute value of A is 2 over Z plus W, absolute value of Z plus W. Now we know the absolute value of A is 12K, so we can substitute it in and get the absolute value of Z plus W. Now we can get the absolute value of all the other quantities that appear in our final expression. So the absolute value of W plus X is 2 over 16K by using the value of IB. 2 over 14K comes from IC, and 2 over 11K comes from ID. So now that we have all of the expressions we want for our final product, let's just throw everything in. Im over in is the expression with the absolute values that we found. And once we throw in the numbers, the k's cancel out as expected because scaling shouldn't affect the ratio. And that gives us our final answer. Does anybody have any questions about this whole problem? So I'll say that in general, this type of application of complex numbers with the unit circle and tangent formulas and such are mostly only useful in Olympiad geometry when you just want to prove something by bashing it. In the AMI, it's more useful to just use complex numbers for rotation purposes. So if you see a circle on the AMI, you don't necessarily need to set it to the unit circle and dash. It's a good idea to just use simpler expressions and methods. Oh yeah, no, MIN are collinear in general. This is Newton's theorem. You can also prove it using complex numbers and using basically what we have. So actually what we have there, Im over in the final bullet, if you get rid of the absolute values, you just have to show that number is real. If you can show that Im over if you can show that W plus X times Y plus Z all over Z plus W times X plus Y is real, then you can show that MI and then are collinear. And to do that, you can just check that the expression is equal to the conjugate of itself. And you can use that, do that since Wx, Y, Z are on the unit circle. And you can simplify it and you find that the conjugate is equal to itself. So this is a way to use complex numbers to prove that MI and are collinear. Any other comments, questions? Newton's theorem. I'm sure there are probably multiple Newton's theorems, but this one should be fairly well known. So if you do a Google search, you should probably come up with it. If there are any more questions, then we'll end class here now. Thanks everybody for coming.